in exactly 48 hours, at 6 minutes past midnight Coordinated Universal Time, an object that has travelled for 7 billion years across the emptiness between stars will reach the closest point it will ever come to our planet. And at this exact moment, 23 nations on Earth have activated the largest planetary defence drill in recorded history. Think about that for a moment. The timing is so precise, so perfectly aligned, that if you were writing science fiction, your editor would tell you it was too convenient to be believable. But this is not fiction. This is December the 17th, 2025, and the interstellar visitor known as 3I-ATLAS is now closer to your living room than it has ever been to any world in our solar system. What happens in the next 72 hours may reshape everything we thought we understood about our place in the cosmos, about the objects that drift between the stars, and about what our governments have been quietly preparing for while the rest of us were not paying attention. Before we dive deeper into what is unfolding above our heads right now, make sure to like and subscribe to the channel. Let's begin. Now let us talk about what is actually happening in the sky above you at this very moment. 3I-ATLAS is currently 269 million kilometers from Earth. To put that in perspective, that is roughly 1.8 times the distance between our planet and the Sun. It sounds far, and in human terms it is impossibly remote, but in cosmic terms this object is practically brushing against our doorstep. This is the closest any confirmed interstellar object has ever come to Earth during a period when we had the technological capacity to study it properly. The first interstellar visitor, Oumuamua, caught us completely off guard in 2017. By the time we realised what it was already racing away from us, leaving behind nothing but questions and controversy. The second Borisov behaved more like a conventional comet, offering fewer mysteries but also fewer opportunities. 3I-ATLAS is different. 3I-ATLAS arrived with enough warning for us to train every major telescope on Earth and in space directly at it. Hubble has been watching. The James Webb Space Telescope has been watching. The European Space Agency turned its XMM Newton X-ray Observatory toward this object for 20 straight hours. Mars orbiters photographed it as it screamed past the red planet at 19 million miles. Even spacecraft on their way to Jupiter have diverted their instruments to capture whatever data they can before this visitor disappears forever into the outer darkness. And here is where the story becomes genuinely strange. On November the 27th, 2025, just 3 weeks before the closest approach, the International Asteroid Warning Network activated what officials are calling the largest planetary defense exercise ever conducted. This is not a simulation running on computers in a basement somewhere. This is a live, real-time, global operation involving NASA, the European Space Agency, the Japanese Space Agency JAXA, the Indian Space Research Organization, the China National Space Administration, and space programs from 19 additional countries. More than 80 observatories have been formally enrolled in this campaign. Ground telescopes in Hawaii, Chile, Australia, and Spain are feeding continuous data into a unified tracking network. Spacecraft scattered across the inner solar system are contributing observations. The explicit purpose, according to official statements, is to test how quickly humanity can detect, track, and coordinate a response to a high-velocity near-Earth object. The object they chose for this test is 3I-ATLAS. Now, I want to be very precise here, because precision matters when we are discussing something this significant. The official position of every major space agency is that 3I-ATLAS poses absolutely zero threat to Earth. It will pass at nearly twice the distance of the Sun. There is no trajectory that brings it anywhere close to impact. The planetary defense drill is described as an exercise of opportunity, a chance to practice on a real moving target that happens to be passing through. And that explanation is entirely plausible. It makes complete logical sense. If you have an interstellar object transiting your solar system, why would you not use it to stress test your detection and response infrastructure? The timing is convenient, yes, But convenience is not evidence of conspiracy. And yet, there is something about the scale of this operation that gives me pause. The European Space Agency just secured a record €22.1 billion budget, with a significant portion allocated specifically to what they call space resilience initiatives. ESA officials have stated publicly that planetary defence is, and I am quoting directly here, no longer science fiction but a critical skill to hone. They have explicitly referenced the 2029 flyby of asteroid Apophis, an object that will pass close enough to Earth to be visible with the naked eye, as a primary motivation for accelerating these preparations. The drill currently underway includes not just tracking and observation, but simulations of deflection missions inspired by the DART test, civil defence mobilisation protocols, and public communication strategies. And that last element is particularly interesting. Public communication strategies. What exactly does one communicate to the public during a planetary defence scenario, and why would that require international coordination to practice? I'm not suggesting that anyone is hiding an imminent threat. The orbital mechanics of 3I-ATLAS are well understood, confirmed by multiple independent observations, and they show conclusively that this object will sail past us without incident. But I am suggesting that the institutions responsible for protecting our planet are taking this moment very seriously, perhaps more seriously than their measured public statements would indicate. When 23 nations simultaneously activate their space defense infrastructure around an object they insist is completely harmless, it is worth asking what else they might be learning, what scenarios they might be running, and what capabilities they might be testing that have nothing to do with this particular visitor, but everything to do with the next one. Consider the trajectory of 3I-ATLAS for a moment. This object entered our solar system from the direction of the constellation Sagittarius, near the galactic centre. It has been falling toward our Sun for longer than our solar system has existed. The latest estimates suggest it formed approximately 7 billion years ago, making it nearly 3 billion years older than Earth itself. It has spent those billions of years drifting through interstellar space, exposed to cosmic radiation, accumulating damage and transformation at the molecular level. When it crossed into the gravitational influence of our Sun sometime in the distant past, it began accelerating, picking up speed as it fell inward. At perihelion, its closest approach to the Sun on October 29th, it was travelling at over 246,000 kilometres per hour. That is the fastest any object of this type has ever been clocked in our solar system. And now, having whipped around our star, it is heading back out toward the void, carrying with it whatever secrets it brought from that other place, that other time, that other system, where it was born before our world even existed. The December 19th closest approach is not just a milestone, it is a deadline. After this week, 3I-ATLAS will begin fading rapidly as it accelerates away from us. Within months, even our most powerful telescopes will struggle to detect it. By the mid-2030s, it will have crossed back into interstellar space, never to return. Every observation we fail to make now is an observation lost forever. Every question we fail to ask is a question that will never be answered. This is not an object we can revisit. This is not a mission we can launch to catch up with it. At its current velocity, no propulsion system humanity possesses could reach it. We had one window, and that window closes in approximately 72 hours. Which brings us back to the drill. If you were a planetary defense official, and you knew that the next few years would bring increasingly close approaches from potentially hazardous objects, and you had an interstellar visitor conveniently passing through your system at the exact moment when global attention on space threats was at an all-time high, would you not use every second of that opportunity to prepare? Would you not coordinate with every ally, activate every sensor, test every communication protocol, and observe every possible behaviour of an object whose physics you do not fully understand? Would you not want to know exactly how your global infrastructure performs under the pressure of tracking something real, something moving, something that came from a place none of your models were built to predict? That is the generous interpretation. the pragmatic interpretation. The interpretation that assumes our institutions are behaving exactly as competent, forward-thinking organizations should behave when faced with a rare cosmic opportunity. But there is another interpretation, one that lives in the margins of official statements and the timing of classified briefings and the unusual intensity of observation campaigns that seem disproportionate to an object we're told is completely unremarkable. And that interpretation asks a different question entirely. It asks not what we are being told, but what we are being prepared for. 3I-ATLAS will reach perigee at 0602, Coordinated Universal Time on December 19th. That is 6 minutes past midnight if you're watching from London, 1 in the morning if you're in Paris, 7 in the evening on December 18th if you're on the east coast of the United States. On that night, the moon will be new, the sky will be dark, and every telescope that can be aimed at this object will be aimed at this object. The data that flows in during those hours will be analysed for months, perhaps years. And somewhere in that data may be answers to questions we have not yet learned to ask. But the closest approach is only part of this story, because 3I-ATLAS is not behaving the way comets are supposed to behave. It is displaying anomalies that have puzzled researchers since the first images came back from Hubble in July. And the most striking of those anomalies is something that should not exist at all. A structure pointing directly at the sun that now extends further than the distance from Earth to the moon. 23 nations prepare for the unthinkable. The document was buried in the Minor Planet Center's internal bulletin, designation MPEC, 2025 U142. Most people would never see it. Most people would not know where to look. But for those who track these things, for the small community of researchers and observers who monitor the official channels where planetary defense decisions are quietly announced, this bulletin changed everything. It was the formal activation notice for the International Asteroid Warning Network's Comet Astrometry campaign, and it named 3I-ATLAS as the centerpiece of what would become the most ambitious global space defense exercise ever attempted. The International Asteroid Warning Network, known by its acronym ILEON, operates under the umbrella of the United Nations Office for Outer Space Affairs. It exists for one purpose: to coordinate the global response to objects that might threaten Earth. Since its establishment, ILEON has conducted 7 previous observation campaigns, each focused on tracking near-Earth asteroids and refining the methods by which we calculate their trajectories. But the 8th campaign, the one running right now, is fundamentally different. This is the first time ILEON has centered an exercise on an interstellar object. This is the first time they have tested their systems against something travelling at 60 kilometers per second, something that did not originate in our solar system, something whose behaviour cannot be predicted by models built on objects we have studied for decades. The participating agencies read like a roster of every serious space power on the planet. NASA and the Jet Propulsion Laboratory are providing deep space tracking data and coordinating observations from spacecraft scattered across the inner solar system. The European Space Agency has activated its Planetary Defence Office and deployed assets including Mars orbiters and the XMM Newton X-ray Observatory. JAXA, the Japanese Space Agency, has contributed observations from advanced space situational awareness systems. The Indian Space Research Organisation, ISRO, is participating with its own detection and tracking capabilities. Even the China National Space Administration, which rarely shares real-time data with Western agencies, has been identified as a cooperating partner in this exercise. Australia, Canada, Israel, South Korea, and more than a dozen European nations have enrolled their observatories and research institutions. More than 80 individual observers have formally signed up to contribute data. The kick-off meeting in October drew 171 participants, a record for any IAWN campaign. The mid-campaign teleconference on December 9th had over 100 attendees, all focused on a single object hurtling through space at a velocity that defies intuition. But what exactly are they practicing? According to official statements, the primary goal is to exercise the capability of the observing community to extract accurate astrometry from comet observations. Astrometry is the precise measurement of an object's position in the sky. And it sounds technical because it is technical, but the reason it matters is simple. If you cannot accurately determine where an object is right now, you cannot accurately predict where it will be in the future. And if you cannot predict where it will be, you cannot determine whether it poses a threat. For asteroids, this calculation is relatively straightforward. Asteroids are solid, their surfaces are stable, and their brightness comes from reflected sunlight bouncing off rock. But comets are different. Comets are extended bodies surrounded by clouds of gas and dust called comas. The brightest part of what you see through a telescope is often not where the actual nucleus is located. The fuzzy glow of the coma can systematically pull your measurements away from the true centre of mass, introducing errors that propagate through every subsequent orbital calculation. 3I-ATLAS presents this problem in an extreme form. Its coma is enormous, extending hundreds of thousands of kilometres in multiple directions. It has an anti-tail pointing toward the sun that should not exist by conventional physics. It has jets erupting from its surface that create asymmetric brightness patterns. And it is moving faster than any comet we have ever tracked, which means small errors in position translate into large errors in trajectory prediction over time. If ARN wanted to stress test their ability to track a difficult target, they could not have designed a better challenge. But the exercise goes far beyond astrometry. Documents and statements from participating agencies reveal that this campaign includes orbital prediction drills, testing how quickly teams can refine trajectory estimates as new data comes in. It includes anomaly response protocols, practicing what happens when an object behaves unexpectedly. It includes multi-agency coordination exercises, evaluating how fast NASA, ESA, JAXA and their counterparts can exchange information, issue alerts, and reach joint decisions during high uncertainty events. And perhaps most intriguingly, it includes public communication modules specifically designed to address what officials call misinformation and psychological preparedness. That last element deserves careful consideration. Why would a planetary defense exercise need to practice managing public communication? The obvious answer is that any real threat scenario would generate enormous public attention, and agencies would need to communicate clearly and consistently to avoid panic. But the inclusion of misinformation management suggests something more specific. It suggests that officials are aware of the narrative chaos that has surrounded 3I-ATLAS since its discovery, the viral claims about alien spacecraft, the speculation about trajectory changes, the accusations of cover-ups and hidden data. It suggests they are practicing not just how to deliver information, but how to counter competing narratives that might undermine public trust in official assessments. The timing of this preparation is not accidental. ESA has explicitly referenced the 2029 flyby of asteroid Apophis as a driving motivation for accelerating planetary defense capabilities. Apophis is a 370-meter asteroid that will pass within 31,000 kilometers of Earth on April 13th, 2029. That is closer than the orbit of our geostationary satellites. It will be visible to the naked eye as it crosses the sky over Europe and Africa. ESA officials have stated publicly that the entire world will be watching when Apophis passes, and that public interest in planetary defense capabilities will be immense. They're using the 3I-ATLAS campaign, at least in part, to build the infrastructure and experience they will need when that much more dangerous moment arrives. But Apophis is a known quantity. Its orbit has been refined to extraordinary precision. The probability of impact has been calculated at effectively zero. 3I-ATLAS represents something different, something that tests capabilities Apophis never could. It tests our ability to respond to the unexpected, to objects that arrive without warning from directions we were not watching, travelling at speeds that compress our response time to almost nothing. Consider the detection timeline. 3I-ATLAS was first identified on July 1st, 2025. Pre-discovery images were later found going back to June 14th, but operationally we had less than 4 months of warning before it reached perihelion. For an object travelling at its velocity, that warning time is almost nothing. A study published shortly after discovery found that launching a spacecraft to intercept 3I-ATLAS would require a delta V, a change in velocity, of at least 24 kilometers per second. No propulsion system currently in existence can achieve that. If 3I-ATLAS had been on a collision course with Earth, we would have had no ability to deflect it. None. We could have watched it coming, and that is all we could have done. This is the scenario that planetary defense officials do not discuss publicly. The scenario where detection comes too late, where the object is too fast, where all our preparations amount to nothing more than documentation of our own extinction. The 3I-ATLAS campaign is not just about tracking comets. It is about understanding the limits of our capabilities, identifying the gaps in our detection networks, and building toward a future where objects like this do not catch us by surprise. The European Space Agency has deployed 2 new systems that are now central to global early warning strategy. The first is called Meerkat, a ground-based detection network designed to scan large areas of sky for faint, fast-moving objects. The second is called Aegis, a space-based component that will eventually provide coverage of regions that ground telescopes cannot continuously monitor. These systems are not yet fully operational, but the 3I-ATLAS campaign is providing real-world data to calibrate their performance parameters. Every observation of this interstellar visitor is teaching us something about how to find the next one, and there will be a next one. Statistical models suggest that at any given moment, there are approximately 10,000 interstellar objects passing through our solar system. We have detected exactly 3. The Vera Rubin Observatory, the most powerful survey telescope ever built, is scheduled to begin science operations within months. It is expected to discover on average 1 new interstellar object per year. Within a decade, we may have dozens of these visitors catalogued, each one a test case, each one an opportunity to refine our understanding of what drifts through the space between stars. The drill currently underway will run through January 27th, 2026. 2 full months of continuous observation, coordination, and analysis. By the time it concludes, 3I-ATLAS will be well on its way out of the inner solar system, but the lessons learned will remain. The relationships built between agencies will persist. The protocols tested will become standard operating procedures, and somewhere in the data collected during these weeks, there may be insights that determine whether humanity survives its next cosmic encounter. I want to be clear about something. I am not suggesting that 3I-ATLAS itself poses any threat. Every credible analysis confirms that it will pass safely, that its trajectory is well understood, that there is no scenario in which it impacts Earth or any other planet. What I am suggesting is that the response to 3I-ATLAS reveals something important about how seriously our institutions are taking the broader question of planetary defense. 23 nations do not simultaneously activate their space infrastructure for a routine observation. Record budgets are not allocated to resilience initiatives because everything is fine. The language used by officials, phrases like no longer science fiction, and critical skill to hone, carries weight. These are not the words of bureaucrats filling out paperwork. These are the words of people who have looked at the data and concluded that preparation is not optional. The next object to enter our solar system from interstellar space may behave very differently from 3I-ATLAS. It may arrive from a different direction, at a different speed, on a different trajectory. It may give us years of warning, or it may give us weeks. The only certainty is that it will come, and when it does, the decisions we make will depend entirely on the capabilities we have built and the lessons we have learned. Right now, as you listen to this, more than 80 observatories around the world are pointed at the same patch of sky. Spacecraft at Earth, at Mars, and in transit to Jupiter are gathering data on the same object. Government officials from 24 countries are participating in the same coordination calls, and an interstellar visitor that has travelled for 7 billion years is approaching the closest point it will ever reach to our planet. The official story is that this is all routine, an exercise of opportunity, a chance to practice. Maybe that is exactly what it is. But there is something else about 3I-ATLAS that demands attention, something that has puzzled researchers since the very first images arrived, something that challenges our understanding of how comets behave and raises questions that no official press conference has adequately addressed. It is a structure pointing directly at the Sun, growing larger with every passing day, and as of the most recent observations, it now extends further than the distance from Earth to the Moon. The anti-tail that defies every law of physics. When you look at a comet through a telescope, you expect to see a tail. That tail should point away from the Sun, pushed outward by the relentless pressure of solar radiation and the charged particles of the solar wind. This is not a suggestion or a tendency. This is physics. Photons carry momentum, and when they strike the tiny dust particles and gas molecules streaming off a comet's surface, they push those particles backward, away from the light source, creating the luminous trails that have inspired wonder and terror in human beings for thousands of years. Every comet we have ever studied follows this rule. The tail points away from the Sun. Always. 3I-ATLAS has a tail pointing toward the Sun. Let that settle for a moment. An object travelling through our solar system is displaying a structure that extends in the exact opposite direction from what every model predicts, what every observation of every other comet confirms, what the fundamental physics of radiation pressure demands. And this is not a subtle effect visible only in processed data. This anti-tail is enormous. As of December 15th, 2025, it extends approximately 500,000 kilometers from the nucleus of 3I-ATLAS in the sunward direction. That is larger than the average distance between Earth and the Moon. It is visible in amateur photographs taken with backyard telescopes. It has been present in every single image captured since Hubble first observed this object in July, and it has persisted through perihelion, through the closest solar approach, and into the outbound journey that 3I-ATLAS is now undertaking. The first Hubble image, released in August, showed a teardrop-shaped coma with a distinct extension toward the Sun. At the time, some researchers suggested this might be a perspective effect, an optical illusion caused by Earth's viewing angle as we looked at the comet through its own orbital plane. This explanation works for certain solar system comets that occasionally display brief anti-tail features when geometric conditions align just right. But 3I-ATLAS has not stopped displaying this feature. Months have passed. The viewing geometry has changed dramatically. Earth has moved, the comet has moved, the angles are completely different, and the anti-tail remains. It is not a perspective effect. It is a physical structure, a real jet of material extending from 3I-ATLAS toward the Sun, and no one has offered a satisfactory explanation for why it exists. Harvard astrophysicist Avi Loeb has written 3 peer-reviewed papers attempting to explain this phenomenon, and his proposed mechanisms reveal just how strange the situation truly is. In the first 2 papers, co-authored with Eric Quito, Loeb suggests that the anti-tail consists of ice fragments shed from the Sun-facing side of 3I-ATLAS. The idea is that these fragments are large enough to resist being pushed back by solar radiation, at least temporarily. They sublimate, turning from solid ice directly into gas before the radiation pressure can accelerate them significantly. The result is a cloud of evaporating ice particles that lingers in the sunward direction, rather than being swept into a conventional tail. This explanation is plausible, but it requires specific conditions. The ice particles must be precisely the right size, large enough to resist radiation pressure, but small enough to sublimate quickly. The outgassing must be concentrated on the Sun-facing hemisphere. The production rate must be sustained over months to maintain the observed structure. No solar system comet has ever displayed this behavior so persistently or so prominently. The third paper, published on December the 8th, 2025, proposes something even more unusual. Loeb suggests that the anti-tail might consist of a swarm of objects that are not attached to 3I-ATLAS at all, but rather travelling alongside it. According to this hypothesis, 3I-ATLAS is experiencing a small but measurable non-gravitational acceleration, a slight extra push away from the Sun caused by outgassing. Objects nearby that do not share this acceleration would gradually lag behind, falling slightly closer to the Sun and creating the appearance of a sunward extension. If true, this would mean that 3I-ATLAS is not a single comet but a convoy, a collection of objects travelling in loose formation through interstellar space. What would such objects be? Loeb does not claim to know. Rocky fragments perhaps, broken off during some ancient collision. Smaller icy bodies that formed alongside the main nucleus billions of years ago. Or something else entirely. Something that challenges assumptions about what drifts between the stars. The latest images, captured on December 13th and 14th by amateur astronomers in Thailand and California, show the anti-tail more clearly than ever. Using processing techniques called Larsen-Sekanina filters, which enhance subtle structures and cometry images, observers have revealed a narrow linear feature extending from the nucleus toward the lower left of the frame, directly toward the Sun. The feature is not diffuse like a typical coma. It has structure, it has edges. It looks, for lack of a better word, deliberate. I want to be careful here because it is easy to see patterns that do not exist, easy to interpret natural phenomena through the lens of expectation rather than evidence. Comets are messy, chaotic objects. They outgaze unpredictably. They shed material in jets that can point in almost any direction, depending on the distribution of volatile ices beneath their surfaces. The anti-tail of 3I-ATLAS may ultimately have a mundane explanation that simply requires more sophisticated modelling than we have yet applied, but the fact remains that as of today, December 17th, no published model fully accounts for what we are observing. The anti-tail exists. It has existed for months. It is growing, and it should not be there. There is another detail that has emerged from recent observations, something that makes the anti-tail even more perplexing. A paper published this week reports that the anti-tail has been wobbling. Not randomly, not chaotically, but with a period of 7.74 hours, plus or minus about 20 minutes. This wobble appears to track the orientation of the nucleus itself, suggesting that the anti-tail is somehow connected to the rotation of 3I-ATLAS. If the jet producing the anti-tail originates from a specific location on the surface, a pocket of volatile material that only vents when facing the Sun, then the rotation of the nucleus would cause that jet to sweep back and forth like a lighthouse beam. This is actually somewhat reassuring from a conventional physics standpoint. It suggests that the anti-tail is indeed being produced by localized outgassing, rather than some exotic mechanism. But it raises its own questions. Why is this outgassing so much more prominent in the sunward direction? Why has it persisted for so long when similar features in solar system comets are transient? And what is the composition of the material being ejected that allows it to resist the overwhelming pressure of solar radiation? The answer may lie in what 3I-ATLAS is made of, and that composition appears to be unlike anything we have encountered before. Spectroscopic observations by the Very Large Telescope detected nickel vapor in the coma, which is not unusual for comets. But they failed to detect iron in corresponding quantities. In every solar system comet where nickel has been found, iron has been found alongside it in roughly equal proportions. This is expected because nickel and iron tend to occur together in the primordial materials from which comets form. 3I-ATLAS is emitting nickel without iron, a chemical signature that suggests it formed under conditions very different from those that prevailed in our own solar nebula. The James Webb Space Telescope observations revealed another anomaly. The coma of 3I-ATLAS is dominated by carbon dioxide to an extraordinary degree. The ratio of carbon dioxide to water is 7.6 to 1, among the highest ever measured in any comet. Solar system comets typically show much more balanced ratios because they formed in regions where both water ice and carbon dioxide ice were stable. A carbon dioxide-dominated composition suggests that 3I-ATLAS formed very far from its parent star, beyond what astronomers call the carbon dioxide frost line, in a region so cold that carbon dioxide could condense while water remained relatively scarce. But there is more. Analysis of the cosmic ray exposure that 3I-ATLAS has endured over its 7 billion-year journey suggests that its outer layers have been profoundly transformed. The radiation has processed the surface material, breaking molecular bonds, creating new compounds, building up an irradiated crust that no longer resembles whatever pristine ices originally formed in that distant protoplanetary disk. When sunlight finally began heating this crust as 3I-ATLAS approached our sun, the physical and chemical reactions that ensued may have been unlike anything we have observed in comets that have spent their entire existence within the relative shelter of our solar system. This is the context in which the anti-tail must be understood. We are not looking at a typical comet with an unusual viewing geometry. We are looking at an object that formed in an alien environment, travelled through interstellar space for billions of years, accumulated damage and transformation that we cannot fully characterize, and is now responding to solar heating in ways that our models were never designed to predict. The anti-tail may be strange, but everything about 3I-ATLAS is strange. The question is whether that strangeness can be explained by natural processes we simply have not encountered before, or whether something else is going on. Avi Loeb, predictably, has not shied away from suggesting that something else might indeed be going on. In his blog posts analysing the anti-tail, he has raised the possibility that the sunward structure could be a concentrated beam of light rather than scattered particles. If 3I-ATLAS was somehow self-luminous in the sunward direction, it would create exactly the kind of persistent structured feature we observe. Loeb does not claim this is the most likely explanation. He has explicitly stated that natural origins remain the default hypothesis. But he has also argued, repeatedly and publicly, that the scientific community should not dismiss alternative possibilities simply because they are uncomfortable. The mainstream response has been measured skepticism. David Jewett, a UCLA astronomy professor who has spent decades studying comets, has pointed out that large dust particles ejected from the sun-facing side of a comet would naturally linger in the sunward direction because they are less affected by radiation pressure than smaller particles. This is standard cometary physics. It does not require exotic explanations. Other researchers have noted that similar sunward enhancements have been observed in solar system comets, albeit less dramatically and less persistently than in 3I-ATLAS. The debate continues, and it will likely continue until 3I-ATLAS has faded beyond the reach of our telescopes. What we know with certainty is this. An interstellar object is displaying a structure that defies easy explanation. That structure has persisted for months, survived perihelion, and grown to dimensions larger than the distance to the Moon. Multiple hypotheses have been proposed, none fully satisfactory, and in approximately 48 hours, that object will reach its closest approach to Earth, presenting one final opportunity to gather data that might resolve the mystery. But the anti-tail is not the only anomaly. There is something else pulsing from 3I-ATLAS, a rhythmic signal that repeats with clockwork precision every 16 hours, a pattern that one researcher has compared to a heartbeat echoing across the void. A heartbeat pulsing through the void. The light from 3I-ATLAS is not constant. It rises and falls in a rhythm so regular that when researchers first plotted the data, they thought their instruments must be malfunctioning. Every 16.16 hours, the brightness of this interstellar visitor increases by 20 to 40%, holds for a time, then fades back down before beginning the cycle again. The pattern has been repeating since at least July, when systematic observations began. It continued through September as the object approached the Sun. It persisted through October as 3I-ATLAS whipped around perihelion at 246,000 kilometers per hour, and it continues now in December as the object races toward its closest approach to Earth. A paper published in the journal Astronomy and Astrophysics documented this periodicity based on observations from research teams spread across Europe and Africa. They measured the brightness variations carefully, accounting for changes in distance, changes in viewing angle, changes in solar illumination. What remained after all those corrections was unmistakable. 3I-ATLAS is pulsing like a cosmic lighthouse, broadcasting its presence into the darkness on a schedule you could set your watch by. The most straightforward explanation is rotation. If 3I-ATLAS has an elongated shape, its apparent brightness would vary as different cross-sections face Earth during each rotation. This is common for asteroids and has been observed in other comets. A 16-hour rotation period is unusual, but not unprecedented. The amplitude of the variation, however, is harder to explain. For the brightness to change by 40%, the shape would need to be quite extreme, with an axis ratio suggesting a highly elongated or flattened object. Early analyses suggested an axis ratio of about 0.8, but that was based on the assumption that the brightness variations originated primarily from the nucleus. Here is where things get strange. The Hubble Space Telescope images show clearly that most of the light we see from 3I-ATLAS does not come from the nucleus. It comes from the coma, the enormous cloud of gas and dust surrounding the solid core. The nucleus is embedded within this glowing halo, contributing a small fraction of the total light. If the periodic brightness variation came only from the rotating nucleus, the amplitude should be dampened by the steady glow of the coma. The fact that we see such strong variations despite the coma's presence suggests that something else is happening. Avi Loeb has proposed an alternative interpretation. In his analysis, the periodic brightening does not come from the shape of the nucleus rotating in and out of view. Instead, it comes from the jets. The outgassing from 3I-ATLAS is not uniform. It erupts in discrete pulses, concentrated from specific locations on the surface. As the nucleus rotates, these active regions sweep into and out of sunlight, switching on and off like geysers controlled by an orbital clock. Each time a volatile, rich pocket faces the sun, it heats up and explodes outward, flooding the coma with fresh material that scatters sunlight and increases the overall brightness. Then the nucleus rotates, carrying that pocket into shadow, and the eruption subsides until the next cycle begins. Loeb describes this as a heartbeat. The comparison is apt. Every 16 hours, 3I-ATLAS pumps a fresh surge of gas and dust into its coma, inflating the bright cloud around it before letting it gradually dissipate. The coma breathes, the object pulses, and the light curve records each beat with mechanical precision. If this interpretation is correct, it has profound implications for what we are seeing. The jets are not random. They are synchronized to the rotation. They are concentrated in specific regions. And they are powerful enough to modulate the brightness of an object visible across hundreds of millions of kilometers of space. This is not passive outgassing driven purely by solar heating. This is structured activity, perhaps shaped by the internal geology of the nucleus, perhaps influenced by the unique composition of an object that formed in conditions unlike anything in our solar system. The distance that material can travel during one 16-hour cycle is significant. If the outflow velocity is around 440 meters per second, as suggested by James Webb data, then gas and dust ejected at the start of a pulse could reach 25,000 kilometers before the next pulse begins. This creates a dynamic, evolving structure around 3I-ATLAS, a coma that is constantly being refreshed and reshaped by the rhythmic breathing of the nucleus within. Now consider how unusual this is. Solar system comets do vary in brightness. They have outbursts and quieter periods. But this kind of clockwork periodicity, this precise 16-hour rhythm maintained over months of observation, through dramatic changes in solar distance and heating, is not something we typically see. Most comets are messy, unpredictable, chaotic. 3I-ATLAS is orderly. Its heartbeat is steady. And that steadiness raises questions. I want to be clear that natural explanations exist and remain the most probable. The heartbeat could be exactly what conventional models suggest: a rotating nucleus with localized volatile deposits that activate when facing the sun. The unusual regularity could simply reflect an unusually uniform distribution of those deposits, or an unusually stable rotation axis, or some combination of factors that happen to produce a clean signal. We have only studied 3 interstellar objects. Our sample size is absurdly small. We cannot know what is normal for these visitors, because we have almost no basis for comparison. But Loeb, characteristically, has raised the possibility that the heartbeat could be artificial. In his scenario, the pulsing could represent controlled thrust from some kind of propulsion system, a cyclic burn that maintains the object's orientation or adjusts its trajectory in ways too subtle for us to detect directly. He has acknowledged that this is speculative, that no hard evidence supports it, that the natural explanation is overwhelmingly more likely. But he has also argued that science requires openness to unexpected possibilities, that dismissing hypotheses before the data is complete is its own form of bias. The scientific community is largely not engaged with these suggestions, and that reluctance is understandable. Extraordinary claims require extraordinary evidence, and a 16-hour brightness variation does not meet that threshold. Rotating comets are not extraordinary. Localized outgassing is not extraordinary. The burden of proof for anything beyond natural processes is enormous, and nothing observed so far comes close to meeting it. What the heartbeat does provide is a window into the internal structure of 3I-ATLAS. The periodicity tells us something about how the nucleus is organized, where the volatile materials are concentrated, how they respond to solar heating, and how the object's rotation distributes that heating across its surface. Each pulse is a data point. Each cycle reveals something about an object that formed 7 billion years ago in a planetary system we will never visit, carrying chemistry we have never encountered, behaving in ways our models struggle to explain. The observations around closest approach on December 19th will be particularly valuable. As Earth and 3I-ATLAS reach their minimum separation, the object will be brighter and more detailed than at any other point in its journey through our solar system. High-resolution imaging from Hubble and other telescopes may be able to resolve structure within the coma that correlates with the brightness pulses. Spectroscopic observations may detect chemical changes in the gas composition as different regions of the nucleus rotate into view. For a few precious days, we will have our best opportunity to decode the heartbeat. After that, the signal will begin to fade. 3I-ATLAS will accelerate outward, climbing back toward the interstellar void from which it came. The 16-hour rhythm will continue, but we will progressively lose the ability to detect it. By spring, the object will be too faint for most ground-based telescopes. By next year, even Hubble will struggle to see it. And eventually the heartbeat will fall below the noise floor of every instrument we possess, pulsing onward through empty space with no one left to listen. There is something poignant about that. For 7 billion years, 3I-ATLAS has been drifting in silence, emitting nothing, receiving nothing, unknown to any intelligence anywhere in the universe. Then, for a few brief months in late 2025, it passed close enough to a star to wake up. Its ices began to sublimate, its jets began to fire, its heartbeat became detectable across the gulf of space. And for this tiny window of time, a species on a small planet orbiting a modest star was able to listen, to measure, to wonder. That window is almost closed. In a few billion years, 3I-ATLAS may pass near another star and briefly wake again. Perhaps by then there will be someone there to hear it. Perhaps they will detect the same 16-hour rhythm and ask the same questions we are asking now. Or perhaps 3I-ATLAS will drift forever without another encounter, its heartbeat fading into the background radiation of the universe, beating for no one, But we are here, we are listening, and the heartbeat continues. There is more to this story, though, more anomalies that compound the mystery. Because 3I-ATLAS is not just pulsing, it is erupting. Observations from the past 2 weeks suggest that this interstellar visitor is covered in something we have rarely seen anywhere in the solar system, something we call ice volcanoes, and they are more active than anyone expected. Ice volcanoes erupting on an alien world. The images arrived in late November from the Joan Oro telescope in Spain, and they showed something unprecedented. Spiral jets of gas and dust were blasting outward from the surface of 3I-ATLAS, curving as the nucleus rotated beneath them, creating patterns that looked less like typical cometary outgassing and more like the eruptions we see on icy moons in the outer solar system. The researchers who analysed these images reached a striking conclusion. 3I-ATLAS appears to be covered in cryovolcanoes, ice volcanoes that are actively erupting as the object races past our sun. Cryovolcanism is a phenomenon we associate with worlds like Enceladus, the small moon of Saturn that shoots geysers of water ice hundreds of kilometres into space. We see it on Triton, Neptune's captured moon, where nitrogen ice erupts from the surface in dramatic plumes. We suspect it occurs on Pluto and other trans-Neptunian objects, worlds so cold that frozen gases behave like molten rock does on Earth. The mechanism is similar to traditional volcanism, but with ice instead of magma. Internal heat, whether from radioactive decay, tidal forces, or some other energy source, melts frozen volatiles beneath the surface. That liquid or vapour then forces its way upward through cracks and vents, erupting into the surrounding environment with explosive force. For 3I-ATLAS, the trigger is sunlight. As the object approached perihelion, solar heating penetrated deeper and deeper into its ancient frozen surface. When the temperature reached the sublimation point for solid carbon dioxide, around minus 78 degrees Celsius, something dramatic happened. The carbon dioxide ice did not simply evaporate. It appears to have destabilized layers of material beneath it, triggering a cascade of reactions that released far more energy than passive solar heating alone could explain. The research team studying these eruptions proposes a fascinating mechanism. 3I-ATLAS, they argue, has a composition similar to a rare type of meteorite called a carbonaceous chondrite. These are among the most primitive objects in our solar system, remnants from the earliest days of planetary formation, rich in carbon compounds and, crucially, in metals like iron and nickel. When the surface ice of 3I-ATLAS began to melt, the resulting liquid water did not simply evaporate. Instead, it began to corrode the fine metal grains embedded within the cometary matrix. That corrosion released energy, released gases like carbon dioxide and hydrogen, and created a feedback loop that amplified the initial solar heating into something much more violent. This would explain one of the most puzzling aspects of 3I-ATLAS, its sustained and global activity. Most comets develop a protective layer over time, a crust of dust and processed material that insulates the volatile ices beneath and reduces outgassing. This is why old comets tend to be less active than new ones. They have built up armour over repeated passages near the Sun, but 3I-ATLAS shows no evidence of such a protective mantle. Its entire surface appears to be active, venting material from multiple locations simultaneously, as if the crust that should have formed simply is not there. The carbonaceous chondrite model offers an explanation. If the composition of 3I-ATLAS promotes chemical reactions between water and metal, those reactions would continuously disrupt any crust that tried to form. The surface would remain fresh, exposed, vulnerable to solar heating in ways that typical comets are not. The result would be exactly what we observe, an object that lights up dramatically as it approaches the Sun, maintaining high levels of activity far longer than expected. The preprint paper describing these findings was posted on November 24th, and the scientific community is still digesting its implications. If correct, 3I-ATLAS would represent something fundamentally different from solar system comets, an object whose internal chemistry drives its behaviour in ways we have not previously encountered. It would suggest that the protoplanetary disk where 3I-ATLAS formed had a different mix of materials than our own, that the processes of planetary formation around that distant star followed different rules. But there is another possibility worth considering. What if 3I-ATLAS is not unusual at all? What if most interstellar comets behave this way, and we simply have not had the opportunity to observe them closely enough to notice? Our sample consists of exactly 2 comets, Borisov and 3I-ATLAS. Borisov did behave more like a typical solar system comet, but it was also smaller, fainter, and studied with less intensive campaigns. 3I-ATLAS is brighter, closer, and under observation by virtually every major telescope in existence. Perhaps we're simply seeing details in 3I-ATLAS that were always present in interstellar comets, but invisible in our limited previous observations. This is the challenge of working with such a small sample. Every data point carries enormous weight. Every anomaly could be a clue to fundamental differences between interstellar and solar system objects. Or it could be a statistical fluctuation, an outlier that tells us nothing general at all. 3I-ATLAS might be typical of its kind, or it might be a freak of nature. We cannot know without observing more objects like it. The cryovolcanic activity has practical implications for how we interpret other observations. The jets erupting from the surface are not uniform. They emerge from specific locations with specific orientations at specific times during the rotation cycle. This creates the complex asymmetric structure we see in the coma. It influences the periodic brightness variations we discussed earlier. It may even contribute to the mysterious anti-tail, if material preferentially vents from the sun-facing hemisphere and lingers before being swept back by radiation pressure. Understanding where these vents are located and when they are active becomes crucial for modelling the overall behaviour of 3I-ATLAS. The spiral patterns visible in the Spanish telescope images suggest that the jets are persistent features, rooted in specific surface locations that remain active as the nucleus rotates. But the intensity of those jets varies dramatically depending on solar illumination. When a vent rotates into direct sunlight, it erupts violently. When it rotates into shadow, the eruption subsides but does not entirely stop, suggesting that heat stored in the subsurface continues to drive out gassing even without direct illumination. This is different from what we see on icy moons like Enceladus, where tidal heating provides a constant internal energy source independent of solar illumination. 3I-ATLAS is entirely sun-driven. Its cryovolcanism is essentially passive, a response to external heating rather than internal processes. But the chemical reaction suggested by the carbonaceous chondrite model would add a second energy source, converting the initial solar input into additional heat through metal corrosion. This hybrid mechanism, solar plus chemical, might explain why 3I-ATLAS is so much more active than expected. The implications extend beyond this single object. If interstellar comets commonly have metal-rich, chemically active interiors, then their behaviour near stars would be systematically different from solar system comets. They would light up faster, remain active longer, and potentially display the kind of dramatic eruptions we're witnessing now. Future surveys like the Vera Rubin Observatory, which will discover many more interstellar objects, could test this prediction by comparing the activity levels of incoming visitors to their chemical compositions as determined by spectroscopy. There is also a more speculative implication. If the cryovolcanism on 3I-ATLAS involves liquid water, even temporarily, even in small pockets beneath the surface, then this interstellar visitor may be carrying one of the key ingredients for life through the galaxy. The panspermia hypothesis, the idea that life or its precursors could spread between star systems aboard objects like comets, has long been considered speculative but not impossible. An object with active liquid water chemistry, traversing interstellar space for billions of years, would be exactly the kind of vehicle that panspermia requires. NASA's ALMA observations have already detected hydrogen cyanide and methanol in the coma of 3I-ATLAS, both considered important precursor molecules for the origin of life. The presence of these molecules, combined with evidence of internal chemical activity, creates a tantalizing picture. This ancient visitor from another star system is not just a frozen relic, it is chemically alive in some sense, reacting and transforming even now as it passes through the warmth of our solar neighbourhood. I want to be careful not to overstate the case. Detecting life precursors is very different from detecting life. Chemical activity is very different from biological activity. The presence of water, carbon compounds and metals does not mean 3I-ATLAS is inhabited, or that it ever was. But it does mean that the chemistry of life as we understand it can exist on objects that spend billions of years in interstellar space. It means the building blocks are out there, drifting between the stars, potentially seeding new worlds every time an object like this passes through a planetary system. 3I-ATLAS will not impact Earth. It will not deposit its cargo on our planet. But somewhere, someday, objects like it will. They always have. The early Earth was bombarded by comets carrying water and organic molecules, materials that may have contributed to the origin of life here. 3I-ATLAS reminds us that this process is not unique to our solar system. It is galactic in scope. The chemistry of life flows between the stars, carried by ancient messengers that we're only now learning to recognize. The ice volcanoes continue to erupt. The jets continue to spiral outward. And 3I-ATLAS continues toward its rendezvous with Earth's closest approach in just 2 days. But its journey began long before our solar system existed, in an age when the universe itself was still young. To understand where 3I-ATLAS came from, we must travel backward in time 7 billion years, to a galaxy that looked very different from the one we know today. 7 billion years of cosmic radiation, before Earth existed, before the sun ignited, before the cloud of gas and dust that would become our solar system had even begun to collapse. 3I-ATLAS was already ancient. The current best estimates place its age at approximately 7 billion years, plus or minus several billion depending on the analysis. To put that in perspective, our entire solar system is only 4.6 billion years old. 3I-ATLAS formed in a planetary system that lived, evolved, and possibly died while the matter that would become Earth was still scattered across a region of the galaxy we cannot identify. 7 billion years ago, the universe was less than half its current age. The Milky Way was a younger, more chaotic place, still actively merging with smaller galaxies, still forming stars at rates far higher than today. The chemical composition of the galaxy was different. Heavy elements, the metals and complex molecules that form the basis of rocky planets and life itself were less abundant. Stars that formed in that era contained less iron, less oxygen, less of the building blocks that we take for granted in our own cosmic neighbourhood. This matters because 3I-ATLAS carries within it the signature of that ancient era. Its composition, the unusual ratio of carbon dioxide to water, the presence of nickel without iron, the extreme irradiation of its surface layers, all of these features are clues to the environment in which it formed. When we study 3I-ATLAS, we are not just studying a comet, we are looking through a window into the early galaxy, into a time and place that no longer exists anywhere in the universe. A study published in late October analysed James Webb observations of 3I-ATLAS and reached a remarkable conclusion. The object's extreme carbon dioxide enrichment can be explained by billions of years of exposure to galactic cosmic rays. These are not the gentle solar radiation that warms planets and drives photosynthesis. Galactic cosmic rays are the most energetic particles in the universe. Protons and heavier nuclei accelerated to nearly the speed of light by supernova explosions, neutron star collisions, and the turbulent magnetic fields of the galaxy itself. They penetrate deep into any unshielded material, breaking molecular bonds, ionizing atoms and fundamentally transforming the chemistry of whatever they touch. For 7 billion years, 3I-ATLAS has been bombarded by these particles. Unlike comets in our solar system, which spend most of their time in the relatively sheltered Oort cloud, interstellar comets have no refuge. They drift through the galactic disk, exposed to the full intensity of the cosmic ray flux, accumulating damage that compounds over geological time. The researchers estimate that cosmic ray processing has created a deep irradiated crust on 3I-ATLAS, perhaps several meters thick, in which the original icy materials have been transformed into something entirely different, carbon dioxide ice. When exposed to radiation, undergoes a series of chemical changes. The radiation breaks apart carbon dioxide molecules into carbon and oxygen. These fragments then recombine in various ways, creating new compounds like carbon monoxide, formaldehyde, and more complex organic molecules. Over billions of years, this process would steadily alter the chemistry of the outer layers, enriching them in carbon dioxide breakdown products, while depleting water ice and other volatiles through different radiation-induced reactions. When 3I-ATLAS finally approached a star for what may have been the first time in its long existence, sunlight began heating this irradiated crust. The chemistry that had accumulated over 7 billion years suddenly had energy to work with. Volatile compounds that had been locked in the matrix began to sublimate. Chemical reactions that had been frozen in place began to proceed. The result was the extraordinary outgassing we've observed, driven not just by simple ice sublimation, but by the release of radiation-processed materials that exist nowhere in our solar system. This is why 3I-ATLAS behaves differently from Borisov or any solar system comet. It is not just from a different place, it is from a different time, and it carries within it the accumulated damage of eons that our local comets have never experienced. The anti-tail, the unusual composition, the extreme carbon dioxide ratios, the cryovolcanic activity, all of these features may ultimately trace back to the transformative power of 7 billion years of cosmic ray exposure. There is something almost philosophical about this. 3I-ATLAS has been irradiated by the deaths of countless stars. Every supernova that exploded within the galactic disk over the past 7 billion years contributed to the cosmic ray flux that shaped this object. The iron forged in stellar cores, the oxygen produced by nuclear fusion, the energy released in the final moments of massive stars, all of it washed over 3I-ATLAS as it drifted through the void. In a very real sense, this object carries within it the combined influence of stellar generations we will never know. The galaxy through which 3I-ATLAS travelled was not always hospitable. There were periods of intense star formation when the cosmic ray flux would have been much higher than today. There were passages through spiral arms where supernova rates peak and irradiation intensifies. There may have been close encounters with other stars, gravitational perturbations that altered the trajectory of this wanderer without leaving any visible trace. The surface we see today is a record of all these events, a geological and chemical history spanning more than half the age of the universe. Researchers have attempted to trace the path of 3I-ATLAS backward through time, identifying which stars it might have passed near in the past 10 million years. They found 25 candidates, stars that came within about 1 parsec of the object's reconstructed trajectory. But 10 million years is nothing compared to 7 billion. The vast majority of 3I-ATLAS's journey remains completely unknown, a dark interval during which almost anything could have happened. Here is where speculation becomes irresistible. If 3I-ATLAS formed in a planetary system 7 billion years ago, what was that system like? Did it have planets? Did any of those planets develop conditions suitable for life? If life did arise there, could some trace of it, some fossilized microbe or organic signature, still exist within the pristine interior of 3I-ATLAS, shielded from cosmic rays by the layers of ice above? The answer is almost certainly no. The radiation exposure would have destroyed any complex organic structures. The heating during this solar passage has disrupted the outer layers, where any such traces might have been preserved. Even if 3I-ATLAS once carried evidence of life from its parent system, that evidence is likely gone now, processed into unrecognizable chemistry by the same cosmic rays that transformed everything else. But the idea persists because it touches something deep in our curiosity about the universe. 3I-ATLAS is a messenger from another world, another time, another history entirely disconnected from our own. The parent star that warmed it during its formation has probably died by now, either collapsed into a white dwarf or exploded as a supernova or faded into a cold remnant that produces no light at all. Whatever planets orbited that star, whatever histories played out on those worlds, are completely inaccessible to us. 3I-ATLAS is the only surviving witness. The data we collect during this passage represents our only chance to interrogate that witness. Every spectrum tells us something about the original composition of the protoplanetary disk. Every measurement of the coma chemistry reveals how those original materials were processed over billions of years. Every image of the jets and coma structure shows how an ancient irradiated object responds to conditions it has not experienced since before the Sun existed. The James Webb Space Telescope is scheduled to observe 3I-ATLAS again this month, after its perihelion passage. These will be some of the most valuable observations of the entire campaign, catching the object as it remains highly active, but has moved far enough from the Sun to reduce the observational challenges of solar glare. Hubble will continue monitoring. Ground-based telescopes will track the fading brightness, and slowly, over the coming months and years, researchers will piece together a portrait of an object that has travelled further and longer than any comet we have ever studied. There is one more observation that deserves mention. In late November and early December, 2 X-ray telescopes turned their instruments toward 3I-ATLAS and captured something never before seen: the first X-ray images of an interstellar comet. What they found adds another layer to the mystery, another piece of data that does not quite fit the expected patterns. Another reason to keep watching as this ancient wanderer prepares for its closest encounter with Earth. The X-ray glow that changed everything. On December 3rd, 2025, the European Space Agency's XMM Newton spacecraft trained its sensitive cameras on a patch of sky in the constellation Leo and held that position for 20 consecutive hours. The target was 3I-ATLAS, and the instrument was the European Photon Imaging Camera, the most sensitive X-ray detector in the telescope's arsenal. What emerged from that marathon observation session was the first X-ray image of an interstellar comet ever captured, and it immediately raised questions that astronomers are still working to answer. The image shows 3I-ATLAS as a bright red glow against the dark blue background of empty space. The red indicates low-energy X-rays, photons with wavelengths far shorter than visible light, far more energetic than the radiation our eyes can detect. These X-rays should not exist. Comets do not generate X-rays through any internal process. They are cold, inert objects, lacking the nuclear reactions or extreme temperatures required to produce high-energy radiation. And yet there it was, a clear X-ray signature emanating from this interstellar visitor as it raced through our solar system. The explanation lies not in the comet itself, but in what surrounds it. As 3I-ATLAS passes through the inner solar system, it sheds enormous quantities of gas, water vapor, carbon dioxide, carbon monoxide, and other volatile compounds that sublimate from its frozen surface. This gas streams outward, forming the coma that surrounds the nucleus. At the same time, the solar wind, that constant stream of charged particles flowing outward from the Sun at hundreds of kilometers per second, slams into this expanding gas cloud. When solar wind particles collide with the neutral atoms and molecules in the coma, something remarkable happens. The fast-moving solar wind ions capture electrons from the cometary gas in a process called charge exchange. This capture leaves the solar wind particle in an excited state, and as it relaxes back to its ground state, it releases energy in the form of X-rays. The entire coma becomes a diffuse X-ray source, glowing in wavelengths invisible to our eyes, but perfectly detectable by instruments like XMM Newton. This process has been observed in solar system comets before. It is well understood physics, but 3I-ATLAS is the first interstellar comet to be detected in X-rays, and the observation provides unique information about its composition that other wavelengths cannot offer. X-ray emission is particularly sensitive to certain elements. Hydrogen and nitrogen, for example, produce characteristic X-ray signatures when involved in charge exchange. These elements are notoriously difficult to detect with optical or infrared telescopes, but they light up clearly in X-ray observations. This matters because one of the great mysteries about the first interstellar object, Oumuamua, was whether it might have been composed of exotic ices like frozen nitrogen or hydrogen. Some researchers proposed that Oumuamua was a fragment of a nitrogen ice glacier from a Pluto-like world in another solar system. Its unusual acceleration caused by nitrogen sublimation rather than water or carbon dioxide outgassing. Others suggested frozen hydrogen as a possible explanation. Both hypotheses remained untestable, because Oumuamua was never observed in X-rays. By the time anyone thought to look, it had already left the inner solar system. 3I-ATLAS gives us the chance Oumuamua denied. The X-ray observations can reveal whether hydrogen or nitrogen are present in significant quantities, providing direct evidence about the composition of an interstellar object that would otherwise remain hidden. If 3I-ATLAS shows the same chemical signatures as solar system comets, it suggests that interstellar visitors are not fundamentally different from our local population. If it shows anomalies, particularly in excess of hydrogen or nitrogen, it could support the exotic ice hypotheses that have been proposed for Oumuamua. The XMM Newton data is still being analysed, and full results have not yet been released, but preliminary reports indicate that 3I-ATLAS is glowing in X-rays exactly as predicted for a comet interacting with the solar wind. The detection itself is the historic milestone. Never before have we caught an interstellar object in this particular wavelength. Every major space telescope, every ground observatory, every wavelength from radio to X-ray has now been trained on this single object. 3I-ATLAS may be the most thoroughly observed comet in human history. Just a few days before the XMM Newton observation, another X-ray telescope captured its own historic image. XRISM, a Japanese X-ray astronomy satellite, observed 3I-ATLAS using its soft X-ray telescope called X-TEND. The resulting image, released alongside the ESA observation, shows a similar diffuse glow, confirming the detection and providing an independent data point for calibration and analysis. What makes these X-ray observations particularly valuable is their complementarity with other wavelengths. The James Webb Space Telescope has provided infrared spectra revealing carbon dioxide, water and carbon monoxide. Optical telescopes have captured the structure of the coma and jets. Ultraviolet observations have detected the breakdown products of water, and now X-rays complete the picture, revealing the interaction between the solar wind and the cometary gas in real time. Each wavelength sees something different. Each provides unique information. Together, they create a three-dimensional portrait of an object that would be invisible in any single wavelength alone. This is why the 3I-ATLAS campaign has involved so many different instruments. This is why agencies from 23 countries have contributed observations. The science requires breadth as well as depth, variety as well as intensity. The X-ray glow also reveals something about the structure of the coma. Because X-rays are produced by the interaction of solar wind with cometary gas, the brightness distribution in an X-ray image traces the density of that gas at different distances from the nucleus. Where the coma is thick, X-ray emission is strong. Where it is thin, emission fades. The XMM Newton image shows that 3I-ATLAS has a substantial extended coma. confirming what optical observations had already suggested, but providing independent verification through an entirely different physical process. There are subtleties in the data that researchers are still working to understand. The exact energy spectrum of the X-rays carries information about which elements are producing the emission. The spatial distribution of brightness can reveal asymmetries in the coma structure, potentially correlating with the jets and anti-tail observed at other wavelengths. The time variability of the X-ray flux, if any, could connect to the 16-hour brightness pulsations seen in optical observations. All of this analysis takes time. X-ray data is notoriously difficult to work with, requiring careful calibration and background subtraction to extract meaningful signals. The 20-hour integration time used by XMM Newton was necessary precisely because 3I-ATLAS is faint, far fainter in X-rays than the bright sources that these telescopes typically observe. Pulling signal from noise is a painstaking process, and the full scientific results may not emerge for months. But the image itself, that red glow against the dark blue void, carries meaning beyond the numbers it encodes. It is proof that we can see interstellar objects in wavelengths that reveal their deepest secrets. It is validation of the multi-wavelength approach that planetary science has embraced. It is a reminder that every tool we build, every instrument we launch, every new way of seeing the universe potentially reveals phenomena we could never have discovered otherwise. The timing of the X-ray observations was not accidental. December 3rd placed 3I-ATLAS at about 282 million kilometers from Earth, close enough for detection but far enough from the Sun to minimize interference from solar X-ray emission. By mid-December, the object has moved even closer, but it is also now far enough past perihelion that its outgassing may be starting to decline. The X-ray window, like so many windows in this campaign, was narrow and had to be used precisely when conditions were right. In less than 2 days, 3I-ATLAS will reach Perigee, its closest approach to Earth. The X-ray telescopes will not be observing at that moment. Their science was done earlier, when the geometry was optimal and the exposure time could be long. But other instruments will be watching. Ground telescopes across the planet will track the object through the new moon darkness. Space-based observatories will capture data that will take months to fully analyze. And somewhere in that torrent of information may be answers to questions we have been asking since July. But the questions about 3I-ATLAS do not originate solely from space agencies and professional astronomers. They have been amplified, complicated, and occasionally distorted by one particular voice, a Harvard astrophysicist who has made it his mission to ensure that we do not close our minds to possibilities that mainstream science finds uncomfortable. His name appears in nearly every discussion of this interstellar visitor, and his interpretations have shaped public perception in ways that the scientific community struggles to counteract. What Avi Loeb refuses to stay silent about his name is Abraham Loeb, though he goes by Avi, and he holds one of the most prestigious positions in American astronomy. He is the head of the Galileo Project, the founding director of Harvard University's Black Hole Initiative, the director of the Institute for Theory and Computation at the Harvard Smithsonian Center for Astrophysics, and a former chair of the astronomy department at Harvard. His publication list runs to hundreds of peer-reviewed papers. His credentials are beyond question, and yet, within the astronomical community, he has become a deeply polarizing figure, a scientist who many colleagues view with a mixture of respect for his intellect and frustration with what they perceive as his relentless promotion of ideas that the evidence does not support. Avi Loeb believes that we should take seriously the possibility that 3I-ATLAS is not natural. Let me be precise about what that means and what it does not mean. Loeb has never claimed that 3I-ATLAS is definitely an alien spacecraft. He has repeatedly stated that natural explanations are overwhelmingly more likely. He has acknowledged that the object behaves in many ways like a comet, that it has a coma, that it outgasses, that its trajectory is consistent with gravitational dynamics. But he has also argued persistently and publicly that the scientific community has been too quick to dismiss alternative hypotheses, too eager to conclude that 3I-ATLAS is ordinary before the data is complete, too influenced by what he calls sociological pressures to conform to accepted narratives. This is the same argument he made about Oumuamua in 2017, and it generated enormous controversy then. Oumuamua displayed unusual characteristics, an extreme elongated shape, an acceleration away from the sun that could not be explained by gravity alone, a lack of visible outgassing. Loeb co-authored a paper suggesting that these features were consistent with a light sail, an artificial structure designed to be propelled by radiation pressure. The paper was technically rigorous, exploring the physics of how such an object would behave, but its conclusion that Oumuamua might be technological in origin sparked a backlash that continues to this day. Critics pointed out that natural explanations existed for every anomaly Oumuamua displayed. The elongated shape could result from collisional history or tidal disruption. The non-gravitational acceleration could come from outgassing of volatile compounds like nitrogen or hydrogen that would be invisible to our instruments. The lack of a visible coma could simply mean that Oumuamua was depleted of the ices that produce cometary tails. None of these explanations required invoking aliens. Occam's razor, the principle that simpler explanations should be preferred over complex ones, strongly favoured natural origins. Loeb responded that Occam's razor should not be used to exclude hypotheses before they are tested. He argued that dismissing the technological hypothesis was itself a kind of bias, a sociological rather than scientific judgment. He pointed out that we have no prior probability for the abundance of technological artifacts in interstellar space because we have never looked. The absence of evidence, he insisted, is not evidence of absence. This philosophical debate has now transferred to 3I-ATLAS, and Loeb has applied the same framework. He has catalogued what he calls anomalies, features of the object that do not fit neatly into conventional models. The anti-tail that points toward the sun, the extreme carbon dioxide ratio, the 16-hour brightness periodicity, the non-gravitational acceleration, the unusual nickel to iron ratio, the extreme irradiation signature. Each of these, he argues, deserves investigation rather than dismissal. On his widely read blog, Loeb publishes almost daily updates about 3I-ATLAS, analysing new images, proposing theoretical explanations, and occasionally speculating about what it would mean if the anomalies turned out to be artificial. These posts reach a massive audience. An analysis by the University of Washington found that of 700,000 posts on X about 3I-ATLAS, approximately 40% mentioned aliens or extraterrestrial technology. More than 130,000 posts mentioned Loeb by name, and 63% of those connected him explicitly to the alien hypothesis. This visibility has made Loeb a target for criticism from colleagues who believe his speculation is irresponsible. Jason Wright, an astronomer at Penn State who himself works on technosignatures and the search for extraterrestrial intelligence, has written detailed rebuttals of Loeb's claims about 3I-ATLAS. He argues that Loeb consistently overstates anomalies, downplays natural explanations, and frames the debate in ways that unfairly suggest mainstream scientists are closed-minded rather than appropriately skeptical. The specific criticisms are technical and detailed. When Loeb suggested that the lack of a traditional tail meant 3I-ATLAS might not be outgassing normally, Wright pointed to images clearly showing cometary structure. When Loeb proposed that the anti-tail might be a beam of self-generated light, other researchers noted that similar sunward enhancements have been observed in solar system comets and can be explained by large dust particles that resist radiation pressure. When Loeb highlighted the unusual composition, planetary scientists emphasized that we have only studied 3 interstellar objects and cannot know what is normal for this population. At the NASA press conference on November 19th, officials explicitly addressed the alien speculation. Associate Administrator Amit Kshatriya stated directly that 3I-ATLAS is a comet, that it looks and behaves like a comet, and that all evidence points to it being a comet. The choice of language was deliberate. NASA was attempting to counteract a narrative that had grown far beyond what the scientific evidence supported, a narrative that Loeb had helped to amplify even while maintaining technical accuracy in his specific claims. Loeb responded on his blog with what some perceived as frustration. He criticised the press conference for not addressing the anomalies he had identified. He questioned why NASA had not mentioned the anti-tail mystery. He suggested that the agency was prioritising public relations over scientific transparency. The exchange highlighted the deep tension between Loeb's approach and the institutional caution of major space agencies. I want to try to be fair to both sides of this debate, because both sides have legitimate points. Loeb is correct that anomalies deserve investigation. He is correct that prior assumptions can bias scientific interpretation. He is correct that we have almost no data on interstellar objects and should be humble about our conclusions. The history of science is filled with cases where mainstream opinion was wrong, where anomalies dismissed as insignificant turned out to be revolutionary. But the critics are also correct that extraordinary claims require extraordinary evidence. They are correct that natural explanations should be exhausted before invoking artificial ones. They are correct that amplifying alien hypotheses to mass audiences, even with careful caveats, can contribute to misinformation and erode public trust in scientific institutions. The social responsibility of scientists includes not just being technically accurate, but being aware of how their words will be interpreted and used. The debate around Loeb has become almost as interesting as the debate around 3I-ATLAS itself. It raises questions about how science should communicate uncertainty, how much speculation is appropriate in public discourse, and who gets to define the boundaries of legitimate inquiry. Loeb sees himself as a champion of open-minded science, willing to consider possibilities that his colleagues find uncomfortable. His critics see him as someone who has strayed from rigorous standards in pursuit of publicity and book sales. The truth probably lies somewhere in between. Loeb is not a crank. His scientific work is generally sound. His specific analyses of 3I-ATLAS anomalies are technically defensible, even when his interpretations are disputed. But he has also positioned himself as a provocateur, someone who deliberately challenges consensus and courts controversy. This positioning has made him enormously influential in public discussions of interstellar objects, but it has also marginalized him within parts of the professional community. What matters for our purposes is not whether Loeb is right or wrong about 3I-ATLAS. What matters is that his questions have forced everyone to look more carefully, to document anomalies that might otherwise have been dismissed, to consider alternative hypotheses that might otherwise have been ignored. Even if 3I-ATLAS turns out to be a completely natural comet, the scrutiny it has received because of Loeb's advocacy will have produced better science, more thorough documentation, and a clearer understanding of what we do and do not know. In approximately 36 hours, 3I-ATLAS will reach its closest point to Earth. The data collected during that window will not settle the debate. It will probably raise new questions as fast as it answers old ones. But it will add to the permanent record of what this interstellar visitor showed us during its brief passage through our cosmic neighbourhood. And that record, more than any individual interpretation, is what will ultimately matter. The moment of closest approach is approaching rapidly. December the 19th, 2025 at 6 minutes past midnight Coordinated Universal Time. The circumstances of that moment, the alignments and coincidences that frame it, deserve a closer look. December the 19th at 06:02 UTC. The mathematics of orbital mechanics are unforgiving. They do not care about human schedules, about convenience, about what we wish would happen. They simply describe trajectories, calculate positions, predict where objects will be at any given moment with a precision that borders on the absolute. And according to those mathematics, 3I-ATLAS will reach perigee, its closest approach to Earth, at exactly 06:02 Coordinated Universal Time on Friday, December 19th, 2025. At that moment, the interstellar visitor will be approximately 268.9 million kilometers from our planet. That distance is large by human standards, roughly 1.8 times the distance between Earth and Sun. You could not reach it with any spacecraft we currently possess. You could not see it with your naked eye even under perfect conditions. But by the standards of interstellar space, by the standards of an object that has travelled for 7 billion years across distances measured in light years, this is intimate. This is practically touching. The timing carries additional significance that observers have not failed to notice. December 19th falls during a new moon phase. The sky will be dark. There will be no lunar glare to wash out faint objects or complicate long exposure photography. Mother Nature, as Avi Loeb noted in one of his blog posts, is being kind to Earthlings, offering optimal viewing conditions precisely when they matter most. 3I-ATLAS will be located in the constellation Leo, high in the pre-dawn sky for observers in the Northern Hemisphere. It will be visible, technically, to anyone with a telescope of sufficient aperture, though visible is perhaps too generous a word. The object is currently around magnitude 11 or 12, which means it is roughly 100 times fainter than the faintest stars visible to the unaided eye. You would need at least a 6-inch telescope and very dark skies to spot it visually, and even then it would appear as nothing more than a faint fuzzy smudge. For astrophotographers with tracking mounts and sensitive cameras, 3I-ATLAS offers more rewarding targets. Long exposures can capture the structure of the coma, the jet spiralling outward, perhaps even hints of the enigmatic anti-tail. Images from the past few weeks have shown the object with a distinct greenish tint, evidence of diatomic carbon being excited by solar radiation. The green glow is a recent development, appearing only after perihelion, another indication that 3I-ATLAS continues to evolve as it interacts with our solar environment. The professional observatories will not rest during this window. The Virtual Telescope project in Italy has scheduled a free live stream beginning at 11 p.m. Eastern Time on December the 18th, 4 a.m. GMT on December 19th. Viewers anywhere in the world with an internet connection will be able to watch in real time as 3I-ATLAS reaches its closest point to Earth. Other observatories across multiple continents will be gathering data, their results feeding into the International Asteroid Warning Network campaign that continues to track this object with unprecedented intensity. The James Webb Space Telescope is scheduled to observe 3I-ATLAS again this month, though the exact timing of those observations has not been publicly released. Hubble will continue its monitoring campaign. Ground-based spectroscopic facilities will attempt to detect changes in the chemical composition of the outgassing as the comet moves further from the Sun. Every major instrument that can see the object will be looking, capturing data that will fuel research papers for years to come. But there is something else about December 19th that deserves attention. It falls almost exactly in the middle of the planetary defense exercise that began on November 27th and runs through January 27th. The closest approach is not just an astronomical event, it is the centerpiece of the most ambitious global space defense drill ever conducted. 23 nations coordinating observations, testing protocols, evaluating their ability to track and characterize a fast-moving object from another star system. The exercise has already produced measurable results. ESA reported that observations from the ExoMars Trace gas orbiter at Mars, combined with ground-based data, improved the predicted trajectory of 3I-ATLAS by a factor of 10. This is extraordinary. We know where this object will be, where it has been, and where it is going, with precision that would have been impossible even a decade ago. The combination of spacecraft at different vantage points, ground telescopes across multiple continents, and sophisticated orbital modelling has created a tracking capability that represents the cutting edge of planetary defence. The question that exercise participants are really asking, though, is not about 3I-ATLAS specifically. It is about the next object, the one we have not discovered yet, the one that might not give us 5 months of warning before closest approach. How quickly can the global network detect a fast-moving target? How rapidly can preliminary observations be refined into accurate trajectories? How efficiently can data flow between agencies that do not always share information smoothly? How well can public communication strategies manage the inevitable speculation and misinformation that accompanies any unusual astronomical event? These are the questions that keep planetary defense officials awake at night. 3I-ATLAS is harmless. Its trajectory is well characterized. There is zero probability of impact, but it is travelling at 60 kilometers per second. If an object like this were discovered on a collision course with Earth, the warning time could be measured in weeks, not months. The DART mission demonstrated that we can deflect an asteroid if we have enough notice, but enough notice requires early detection, rapid characterization, and global coordination. The 3I-ATLAS campaign is stress testing all of those capabilities simultaneously. The results so far have been encouraging. The International Asteroid Warning Network has functioned as designed, with more than 80 observers contributing data to a unified tracking effort. Agency coordination has been smooth, with ESA, NASA, JAXA, and others sharing observations in near real time. The public communication challenge has been more difficult, with alien speculation overwhelming factual reporting in many online spaces, but this too is a learning opportunity. The next time an unusual object appears, agencies will have a better understanding of how narratives form and spread, and how to counteract misinformation before it takes root. December 19th will test these systems one final time before 3I-ATLAS begins to fade beyond easy observation. The data collected during closest approach will be some of the most valuable of the entire campaign, capturing the object at its brightest, its closest, its most detailed. Whatever anomalies remain unresolved, whatever questions remain unanswered, the observations from this window will be the best opportunity to find answers, and then it will be over. Not immediately, not dramatically, but steadily and inexorably. 3I-ATLAS will continue outward, climbing away from the sun, accelerating back toward the interstellar void from which it came. By March, it will pass within about 53 million kilometers of Jupiter. Close enough for a gravitational interaction, but not close enough to significantly alter its trajectory. The giant planet will tug on this visitor from another star, and then release it, sending it on its way toward the outer solar system. By the mid-2030s, 3I-ATLAS will cross back into interstellar space, leaving our solar system forever. It will continue travelling, continuing cooling, its ice volcanoes going dormant, its heartbeat fading, its coma dispersing into the vacuum until nothing remains visible but a cold, dark nucleus carrying 7 billion years of history into the endless night. We will not see it again. No human being, no successor species, no future civilization that might arise on Earth or elsewhere in our solar system will ever have another opportunity to study this particular object. It came from a place we cannot identify, formed in conditions we can only infer, and carried with it secrets we may never fully decode. For a few brief months it passed close enough to examine. That window is almost closed. But there is one more element to this story, one more layer of meaning that I have been building toward throughout this discussion. It concerns the timing, the coincidences, the alignments that have characterized this entire event from the moment 3I-ATLAS was discovered. Because when you step back and look at the full picture, when you consider everything that is happening simultaneously, the word coincidence begins to feel inadequate. When coincidence becomes too perfect, I want to lay out the timeline of what has happened over the past 6 months, not to argue for any particular conclusion, but simply to let you see the pattern as it has unfolded. You can draw your own conclusions about what it means. July 1st, 2025. The ATLAS telescope in Chile detects a faint object moving against the background stars. Within days, astronomers confirm its trajectory is hyperbolic. It came from interstellar space. It is only the third such object ever confirmed. August. The Hubble Space Telescope captures the first detailed images. They reveal a teardrop-shaped coma with an extension toward the Sun an anti-tail that should not exist. The James Webb Space Telescope follows with infrared observations showing extreme carbon dioxide enrichment, unlike anything seen in solar system comets. September. 3I-ATLAS approaches Mars. ESA's Mars Express and ExoMars orbiters capture images from a distance of less than 30 million kilometers. The composition continues to puzzle researchers. Nickel without iron, methanol and hydrogen cyanide, precursors to the chemistry of life. October. The comet reaches perihelion, whipping around the Sun at nearly 250,000 kilometers per hour. Solar observatories track it through the glare. When it emerges on the other side, it has changed. The coma is larger, the activity is more intense. The green glow of diatomic carbon has appeared. November. NASA holds a press conference explicitly addressing alien speculation, confirming that 3I-ATLAS is a comet, nothing more. The same week, the United Nations International Asteroid Warning Network activates its largest ever planetary defense campaign. 23 nations participate. ESA secures a record budget with expanded funding for space resilience. Officials state publicly that planetary defense is no longer science fiction. December. X-ray telescopes capture the first ever X-ray images of an interstellar comet. Amateur astronomers document the anti-tail extending to 500,000 kilometers. The heartbeat pulsation continues its 16-hour rhythm. The cryovolcanic eruptions persist. And on December 19th, 3I-ATLAS reaches its closest approach to Earth, passing within 269 million kilometers during a new moon, offering optimal observation conditions precisely when they are needed most. Now consider the coincidences. The third interstellar object ever discovered arrives just as humanity has developed the technological capability to study it comprehensively. It approaches Earth's orbit at a time when every major space telescope is operational and able to observe. It reaches closest approach during a new moon phase that minimizes observational interference. Its passage triggers the largest planetary defense exercise in history, stress testing the very systems that would be needed if a future object posed an actual threat. And this exercise runs from late November through late January, bracketing the closest approach perfectly, as if the timeline were designed by a committee. I'm not suggesting that any of this was planned. I'm not claiming that 3I-ATLAS is anything other than what NASA says it is, a natural comet from another star system, remarkable but not supernatural. The coincidences I have listed are coincidences. They can be explained by the laws of probability, by the fact that we observe what we are capable of observing, by selection effects that make certain events more likely to come to our attention. But there is something about the perfection of this alignment that invites wonder. An object older than our solar system, travelling for 7 billion years through the galaxy, arrives at this exact moment in human history. We happen to be at exactly the right technological level to see it, to study it, to learn from it. We happen to have instruments in space, at Mars, in transit to Jupiter, all of which can contribute observations. We happen to have global coordination mechanisms in place to share data and collaborate across national boundaries. Everything lines up. Perhaps this is what the universe does. Perhaps interstellar objects pass through our solar system constantly, tens of thousands of them at any given time according to statistical models, and we simply never noticed before because we lack the tools. Perhaps 3I-ATLAS is not special at all, just the first member of a vast population that we are finally able to perceive. Perhaps in 10 years, after the Vera Rubin Observatory has discovered dozens more, we will look back at our current fascination and find it quaint. Of course, interstellar visitors exist. Of course they pass through regularly. What did we think the galaxy was? Empty. But for now, in December 2025, 3I-ATLAS feels special. It feels like a message, even if we cannot read the language. It feels like an invitation, even if we do not know where we are being invited. It carries chemistry that we recognize, carbon and water, and the building blocks of life. It displays behavior that we cannot fully explain. It arrives precisely when we are prepared to notice, and it departs just as we are learning to understand what we are seeing. I do not know what to make of that. I'm not sure anyone does. What I do know is that the next 48 hours will be crucial. The data collected during closest approach will be analysed for months, perhaps years. Researchers will publish papers debating the anti-tail, the heartbeat, the cryovolcanism, the composition. Some mysteries will be solved. Others will deepen. And eventually, when 3I-ATLAS has faded beyond our ability to observe, we will be left with whatever conclusions we have managed to reach. Those conclusions will shape how we think about the universe, about our place within it, about the objects that drift between the stars carrying histories we can barely imagine. 3I-ATLAS is a messenger. We may never fully understand the message, but the attempt to decode it has already changed us. As I record these words, the interstellar visitor is closer to Earth than it has ever been, closer than it will ever be again. Telescopes around the world are pointed at the same patch of sky. Space agencies on 6 continents are coordinating observations. An ancient object from another time, another place, another star is passing through our cosmic neighbourhood, offering one final glimpse before disappearing forever into the darkness between worlds. Think about that for a moment. Let it settle. And if you have stayed with me through this entire journey through the science and the speculation, the anomalies and the explanations, the coincidences and the questions they raise, then I want to thank you. This is why I make these videos. This is why I spend hours researching, writing, trying to capture something true about the universe we inhabit. Because moments like this matter. They connect us to something larger than our daily concerns, something older than our species, something more vast than any individual mind can fully comprehend. 3I-ATLAS has been travelling for 7 billion years. It paused in our solar system for a few months, and then it continued on, toward whatever destination lies beyond the reach of any telescope we will ever build. We were lucky to see it. We were lucky to be here, at this moment, with these tools, with this capacity to wonder. If this content meant something to you, please consider sharing it with someone who might appreciate it. Subscribe if you have not already. Leave a comment telling me what you think, whether the coincidences we have discussed feel meaningful or merely random. I read every response and your engagement shapes what I create next. Thank you for watching. Thank you for thinking. Thank you for being part of this community of curious minds trying to make sense of a universe that never stops surprising us. The sky is dark tonight. The moon is new, and somewhere out there, getting closer every minute, an ancient visitor from another star is preparing to say goodbye. Good night, everyone. Keep looking up. Disclaimer. This video contains scientific information alongside speculation and theories that have not been confirmed by mainstream scientific consensus. The views expressed about potential anomalies and alternative interpretations represent ongoing debates within the scientific community. Always consult official sources from NASA, ESA, and peer-reviewed scientific publications for confirmed information about 3I-ATLAS and other astronomical phenomena.